Okay, so my name is Aaron Code. I work at Intel. I work in the developer relations team, specifically for what we call visual computing. So primarily working with gaming and graphics companies around Europe. I'm based here in Munich, Germany. What I'm going to talk to you today is specifically about a library that we put together to make threading easier. Now, the interesting part of that is, rather than us make a big product out of it, we've spent a lot of effort into it, but we've open sourced it as well. So it's available in the open source community for people to contribute to further. We do actually sell it for some people as well if they want to support behind it, but primarily it's focused in the open source community. And I'm going to tell you why I think it's pretty powerful and why it'll make multi-threaded programming a lot easier. So in that respect, I'm going to talk about it in the framework of talking about a game. You know, multi-threading for games is traditionally a very difficult problem. Usually when you do multi-threading for game, you have to do it in a very different way than you would do many other applications. And we'll talk about that a little bit. I'll show you some examples of why that's difficult to do in Windows and pthreads, and then I'll show you why the thread building blocks can do it a lot better, and you'll see the real difference as well. Okay, so usual game structure: render, on-frame mover, update world, whatever you want to call it. It's a pretty cyclical type of thing. Change everything in the world, then render it out to the graphics card. Right? In-frame move usually consists of a bunch of different things like physics, AI, particle systems, etc. Right? There's a demo that we have on our software network that's called Destroy the Castle, where we actually give you both source code and a real kind of graphical demo showing you of how to multi-thread a simple game. The idea is you have a cannon here and you can move it around, you can shoot it against the castle, the bricks fall down. You also have AI characters running around trying to dodge the cannonballs as well. Okay? Now, don't worry about the tool that I'm using to look at the performance analysis, but we can roughly break down the performance from a serial perspective to the render, physics, AI, and particles. So you see render here. Physics takes up a large chunk. AI takes up quite a large chunk as well, and particles a small chunk, relatively. In our particular game structure, we use the particles to simulate the smoke from the cannonball as it's traveling across the screen. Not a large number of particle systems, but a large amount of AI and physics. Okay? So one of the things we did was to thread this with Windows WinThreads or pthreads. Okay? And this is another tool called the Thread Profiler that we work with a lot, which lets you look at the timeline of threads. Okay? Now, interestingly here you can see the yellow transition lines are where you have threads that are signaling, either by an event or by releasing a lock, as an example. The dark green time is where the thread is actually running. The light green time is where that thread is suspended, waiting for some kind of resource. Okay? So, basically you can see that since I don't have a large amount of dark green time on all three threads at the same time, I don't have a lot of concurrency going on in the beginning. So another way we can look at it is we can look at what we call a concurrency profile. Okay? Now this is on a system, it's important to realize this is on a system that has 4 cores. Okay? So concurrency means at concurrency level 4, all 4 threads are running active. So how much of the time, how many threads do I have running? Okay, so on a 4-core system, this is the perfect level to be at, right? Anything less is, okay, I'm not as parallel as I would like to be. Anything more is also bad. I'm oversubscribed. I'm trying to get too many threads running at the same time. Okay, does everybody understand that so far? I'm not going to dig too deep into the particular tool, but this is just an analysis of looking at our little demo. Okay? And here I describe it in a little bit more detail. Serial time is concurrency level 1. Undersubscribed is what we call in the number of cores. Fully parallel or fully subscribed threads equals the number of cores. Oversubscribed threads over cores. Okay. Now, generally speaking, oversubscribed is bad, right? When I have more threads running than the number of cores. Anybody tell me when oversubscribed is not a bad thing?
Could you please? Test.
Exactly.
Good.
When you have a lot of I/O threads. So, I'll give you one here. I have a few things to give away. People answer questions get some things.
Test.
This is actually the O'Reilly book for the thread building blocks. But absolutely right. Generally, what you mean is you want the concurrency level to be fourth CPU bound or compute bound threads, is what we call it. It's okay to have more threads if they're I/O threads, so they're not actually doing a lot of stuff. Okay. So, in the serial execution, right, we have 25% of the system utilized, and this is what it looks like in profile. It's all in concurrency level 1. It's a single-threaded version of our Destroy the Castle demo. Okay? Running it for X number of frames takes us about 21 seconds on a 4-core system. Okay? So, you can imagine as number of cores have been growing in the platforms, and the frequency is not growing, that Intel and a lot of other people in the industry are telling you that, you know, if you want to continue to get additional performance out of the platform, you have to handle it in terms of multiple thread programming. Okay? So you really need to focus on getting that out. Now the challenge when you move from single-threaded programming model to multi-threaded programming model is you'd like to make that switch such that as the number of cores grows, you can scale with that automatically. Okay? Do you guys know data parallelism versus functional parallelism? Okay. So data parallelism is when I have a big chunk of data, let's say an array of 1 million elements, and I can divide that array up into the number of threads I have. Okay? And so each thread does exactly the same computation on all of that data. Okay? Why is that good? Because if I increase the number of threads, i.e. cores, then I just continue to scale. Each thread gets a little bit smaller chunk of the data, but they go through it all the same. Now, there's another one called functional parallelism. Functional parallelism is where you take threads and they do different things. Okay? Think of an assembly line as a good example. Okay? If you have data that's going to be compressed and then it's going to be encrypted, right? So you're streaming data in. So you can have one thread doing the data compression of a chunk of data, passing that on to the next thread and encrypting it, and then passing it out, right? Does that make sense? So 2 threads works great for a 2-core system. Now, what's the challenge? As soon as I add another core to the system, right, I don't have anything for it to do. I've only got 2 tasks for it to do, so I either have to find another task or I have to go back to data parallelism. Now the challenge in games is data parallelism is really difficult. You take a typical scene graph and try to go data parallel on that, and there's so many dependencies all over the scene graph that you've got little chance of getting a good parallelization. Whereas typically what people do is use functional parallelism. Okay? They take the render, they take the AI, they take the physics, and they put it into separate threads. That makes sense? Okay, so we're going to go through that a little bit. So this is exactly what I was talking about. We're going to use parallelization with normal Windows 32 threads. We'll have 1 thread for rendering, 1 thread for physics, 1 thread for AI, 1 thread for particles. Okay? Seems pretty easy. For the most part, it's not a difficult thing to split the game up in this direction. Not super easy, but not so difficult. Okay? And we look at that. Well, now, you remember our graph from before. We were all at concurrency level 1. Get the mouse back here. I was all here before. Now I've got some parallelism. I've got a bunch of time at concurrency level 2, 3, and a very little bit at concurrency level 4. Okay? And if you look at the timeline, you can see all kinds of synchronization going on between them. Now you expect the render thread is going to have to synchronize with everybody, guess what? Every frame, right? So when the frame is done, you're ready to push it out, you're going to have to synchronize with the render thread. So that one you can't get around. But there's some other synchronization going on. If I remember, this guy is the particle thread, right? He's only got a little bit of time. So what's happening here is I don't have a good load balance, right? The physics thread is down here, the AI thread is here, and the particle thread is here, right? So obviously the particle thread isn't taking up a lot of CPU time, while the physics thread takes up more and the AI takes up even more. Okay? That's one of the other downsides of functional parallelism, is that it's very hard to load balance the tasks, right? Some tasks are just going to be this big and some tasks are going to be that big. Okay? But I still got better. I'm still twice as fast, so 2x, but I had 4 cores. So it's really kind of like on the downside in terms of scalability. You know, if the world was perfect, I'd like it to be 4 times as fast as the serial version. Okay? Any questions so far? Does everybody understand why there's a load imbalance? Yeah? Okay? Am I going too fast? No? Okay. Okay, so, you know, makes sense, right? The AI is actually a big, huge chunk. So maybe what I need to do is split up the AI. Maybe now I've got the functional parallelism, I do a nested on the AI, and I do a data parallel on the AI. Okay? So I add a whole bunch more threads just to do AI. Okay? So that's what it looks here. I added a thread pool just for the AI. Right? So now we have here, again, the other 3 here, and the render thread. Right? Looks not too bad. It looks better. Right? My concurrency level at 4 is a bit higher. My concurrency level at 2 and 3, it's okay. It's a little bit less. I have a little bit of oversubscription too. Okay? The problem here is that it gets really hard to get this load balance correctly. Right? You end up having to play with how many threads you give to the AI, how much you break it down in terms of data parallelism, and that gets really hard to do with Windows 32 threads. Okay? And what's worse is the right answer could change from frame to frame to frame. Right? You might not have the same load balance problem on one frame versus the next frame. Okay, so if you figured out for your toughest scene or toughest frame, you needed to have, 3 AI threads, and the next scene, that could be a complete waste. Right? So we got a little bit of improvement when we did that. Here we gave 4 threads to the AI pool, right? Now we have a lot of oversubscription. There's a lot of points and times where we have more than 4 threads running. So if you look, it's right here in particular. Okay? So what I've really done is I've taken my conceptual problem or piece, and I've married it directly to the thread. Right? So I can't split that up easily. That's the problem when you're doing Windows 32 threads and P threads. When you're managing it yourself, you end up kind of one thread equals a task. Right? There's no way to divorce that or make it separate very easily. You can, but you end up writing more or less what we're going to talk about in a minute. And in this case, it was actually slower. Okay? So oversubscription, people think, well, if I just have more threads, the CPU will schedule it all back and forth. But the problem is scheduling threads back and forth costs a lot of time. The OS to do a context switch is, thousands and thousands of clock cycles that you don't want to waste. You'd really rather the threads stay on the core and more or less run without being scheduled out. Okay? Here's a little bit more detail where you see the oversubscription. So, this nested parallelism is kind of the problem. We'd like to be able to do something more like software component model, where you can have one thread specify more parallelism, but do so in a dynamic way. Maybe it decides it's the right time to specify more parallelism. Maybe it decides it's not the right time to specify more parallelism, right? You'd like it to be able to specify this amount, and then we map this to the actual number of threads. Okay? So just to recap some of the problems you have with Windows 32 threads. It's hard to come up with a good design. It maps across all of your usage model. The code usually becomes very dependent on the OS threading facilities. P threads are different than Windows 32 threads. There are some things that can be quite different. You don't have critical sections in Linux. P threads versions are all over the place, more or less, between some platforms, although they've standardized a bit more in the last couple of years. Load imbalance has to be managed manually, right? You cannot count on the OS to do that for you. And many times you end up with an oversubscription problem. Okay? So now, of course, I said why you should never use Windows and P threads. Let me tell you how you ought to do it. So what are the thread building blocks? So Intel, together with a few people in the industry, got together and worked on something called the thread building blocks. It is a layer, or a library, if you will, that abstracts threading. Okay? You specify task patterns instead of threads. You talk about things in terms of tasks, not threads. Okay? So we're going to divorce the concept of our actual task or our work unit from the thread. Okay? We let the thread library handle all the managing of thread to hardware core. Okay? And then specifically, the library is targeted at getting more and more scalability. Okay? So not only that, the tasks are very good, but the synchronization primitives that we put in are really designed to be scalable from 1 to 128 or 512 way. What people have found is they had good multi-threaded designs for 2 cores and 4 cores, but as they ran it on an 8-core or a 16-core system, they found that their design falls apart because things like synchronization become exponentially more costly as you add number of cores and threads. All right? Does everybody understand why that's the case? Why it's more expensive? Okay, so let me ask. Who can explain in a little bit more detail why does synchronization become exponentially more expensive with the number of cores or threads?
Sorry, if you want to ask questions and talk, please do it on the microphone. Because
we have a microphone. Yay. That way we get you recorded and you can be on the internet too.
I don't know exact.
Is
this on? Sorry, I don't know exactly why it's exponential, but if you have some spin lock and you lock it, then each other thread that will run to this spin lock will lock until every thread, the first thread has left the lock, then the second must left, and so you get a serialization of all instructions over every CPU, and the more CPUs you use, the longer you might have to wait in such a lock situation. So
yeah, exactly. So as you have more threads coming to a synchronization point, right? If I go from 8 to 16, I've got double the number of threads coming to that place. So the average time that they're going to have to wait grows relative to the number of threads. So, great answer. There you go. Okay, so let's get into a little bit more of what it really is. It has algorithms, concurrent containers, synchronization primitives, memory allocation, and a task scheduler. Kind of the high-level principles is it uses task patterns instead of threads. Okay, so you don't have to worry about threads. It does something called work stealing, which helps with load balancing. And it does deals with the oversubscription problem by only having one OS thread per processor, per core. Okay? So just to group it all together, we have in the parallel algorithms, there's a parallel for, a parallel while, parallel reduce. There's a pipeline pattern. You know, obviously I can set it up like an assembly line. There's a parallel sort and a parallel scan. In a concurrent containers, we've implemented a concurrent hash and a concurrent queue and a concurrent vector. Quick question. Is STL containers thread safe? No, very bad. You can actually, I think in Microsoft, you can turn one of the switches and you can make the STL containers safe. And you have one lock for all of the containers of all of STL. Therefore, your bottleneck. Okay. Synchronization primitives, there's atomic operations, spin mutexes, queuing mutex, read-write mutex, queuing read-write mutex. So reader-writer is a common synchronization paradigm. And we have memory allocator, a cache-aligned allocator, and a scalable allocator. Okay. Why would I implement a scalable memory allocator? Anybody have an idea? Why is memory allocation a problem for multi-threaded programs? Oh, here comes the microphone.
Also in the normal memory allocation, you have a linked list from free nodes to unused free nodes. And if you have a concurrent update of this allocations and freeze, you have to log the whole linked list of node information, and that might, if you have two threads allocating a lot of small objects, they might just be waiting for this global heap management structure to be locked and unlocked. So
Yep. So you hit on it. So what he's saying is, in memory allocation in C library in most runtimes, there's one lock for malloc, or new. One global lock. So if threads are actively allocating and deallocating stuff, guess what? That becomes a bottleneck very quickly. So a scalable memory allocator, what it does is it creates a memory pool for every thread. And you allocate from that pool instead. So you don't need to synchronize, and two, you get kind of your chunk of memory space. Okay? It comes at a little bit higher memory cost potentially, but the performance is a dramatic difference. Okay? Okay, so now I have another question. I'll get you something in a minute, but there's another part of the C runtime that is notoriously bad at scalability, i.e. there's a global lock on it. Anybody tell me what it is? What do you do when you're trying to debug a multi-threaded program frequently? Printf. Who said printf? There you go. I'll get you a shirt. Guess what? Screen I/O is synchronized. If you start printing out too much stuff in your multi-threaded program, your scalability will drop. That's a very, very interesting thing. People don't realize that because in most of the C runtimes, there's a lock on the screen I/O. Okay? Usually, it's okay. You get through if you're using fprintf, right? You have a stream buffer. But when that buffer goes out to the actual I/O, there's a lock. So when you're doing debugging and when you're doing performance testing, you ought to watch out for how much you're outputting in standard I/O. Okay? Okay, let's get going a little faster. So here's an example. I created a class. This is my task object. It derives from public task. Okay, it has an execute function that I get. Here's it being used in the real world. My root task, you can call it main, Now, I have to do a kind of a funky allocation to allocate this task. Say my task new. The reason you do this, okay, is because you want to make sure that that new task gets included with the scheduler. Okay? It's a little bit of dirty syntax because C++ doesn't have anonymous functions yet. But once we do that, that gets it into the task scheduler. So he understands everything. And then I say spawn my task. Okay? And I can say wait for all. Okay? So right now it doesn't look that much better than a pthreads, right? I've got to do pthread, pass it my function pointer. Okay, but syntactically it's a little different. But here's what happens when I do this. Okay? In my main, initialize the threading library, and it creates a thread pool. Okay? After I allocate my task and I spawn, here I spawn root and wait, creates this task, and he assigns the task to a real thread and starts executing it. Okay? So that's the basic process of initialization. Now, what happens in the real world is I've got a whole bunch of tasks, and I want to create a lot of tasks. So I'm spawning these tasks, and they get assigned to each thread. Each thread has its own queue. Okay? This is a very important principle. Okay? So he assigns it on to the next one, and they're processing all of their tasks. Okay? Does everybody understand? Now, and this is how you deal with load balancing. It's called task stealing. Okay? Task stealing is when one thread runs out, its queue runs empty. He says, well, wait a minute. I'm going to go grab a task from one of the other queues and start working on it. Because if I just let it run empty, then my load balance problem would come right back, right? But now I go grab a task from the other queue. Okay? Now, that's one of the reasons why it's important to specify as many tasks as possible, right? Because that allows the system to automatically balance it much better, sorry. One of the other things that I'm not going to get into here this time, but when you specify tasks, you have the ability to specify that they can be decomposed. So you can specify that this task can be decomposed into smaller subtasks. Okay? So that it can start off as a big chunk, and you let the runtime decide, this big chunk is too big, I've got more threads to run than this, I'll decompose it, and it can decompose quite a bit. Okay? An example of that is if you have an array, you could specify, okay, this array can be divided by half and half and half, and I let the runtime decide how far to do that decomposition. Okay? So for loop parallelism, we have a parallel for and a parallel reduce. Parallel scan lets you do kind of what we call parallel prefix. Y of I equals Y of I minus 1, some operator times another operand. Okay? There are ways to do this in parallel. Typically, you would think of this as not something you could not compute in parallel. But there are some tricks if you follow this specific type of pattern to make that a parallel operation. Then we have parallel while, of course. It gives you an unstructured stream or pile of work. Have a pipeline is nice because you can specify pipeline stages. And each stages could be further one of the other parallel for or parallel scans. And you specify a set of tokens, essentially assigned to the chunks of work that go through the pipeline. Okay? So it's a very native way to do traditional functional parallelism. And there's a parallel sort as well. Okay? Now, the concurrent data collectors provides, well, as I was talking about, traditional STL is not very thread safe. Simple example, if you grab an item in an STL container and another thread deletes it, you can corrupt the container completely. Okay? So you need to be able to deal with those situations. But you don't want a single lock for the entire container at the same time. Okay? So we use a pretty smart implementation of how to deal with that. We use pretty fine-grained locking or double locking situations so that you can get the most amount of parallelism out of the data container. Synchronization primitives, mutex, spin mutex, a queuing mutex. So here's a question. Most synchronization primitives, there's no first in, first out paradigm. This is also one of the problems between Window32 and p-threads. There's no guarantee that the thread as it comes in gets to go out in that same order. Okay? Kind of randomly it can choose the next one to come out. So theoretically, you could have a thread wait indefinitely on a synchronization primitive, both in Windows 32 threads and p-threads. So we explicitly put in a queuing mutex so that you know it's first in, first out. Okay? And a reader-writer, how many people know the reader-writer paradigm? Couple? So reader-writer paradigm is a special situation in parallelism where you have a data structure where you have lots of readers and one or a couple of writers. So the readers, they don't need to synchronize their access to the data structure, right? They're not changing anything. But as soon as you get somebody coming in who wants to write the data structure, then you have to pause, or you have to let everybody finish accessing the data structure, prevent anybody else from coming in, do the write, or let that write task happen, then release it, and then the readers can come in again. Okay? It's a very common paradigm when you don't have a lot of write updates to a data structure, but you have a lot of reading. Okay? That way you get less synchronization costs. Question?
During the write process, the data are locked for reading, or
They're locked for all access, so locked for reading and writing access.
if only one writer is saving some data, all parts are locked.
Correct.
Okay.
What you need to do, right, to ensure that it's correct.
Maybe Microsoft don't that you can read and write at the same time.
Well, you can, if the data that you're talking about is not the same data, then it could read something else in the data structure, potentially. But generally when you're writing, you want to prevent everybody from reading because you're going to update the data structure. And then only once you're done updating, do you want to let the readers come back in. Yep. Thanks for asking a question. Yep. Okay, so I talked a little bit why we have a scalable memory allocator, because there's one lock in the typical C runtime library on memory allocation, so you want to have separate memory pools for each thread. The scalable memory allocator is pretty nice in the system that we have. It also has a cached line memory allocator. Okay? For the last book, who can tell me what false sharing is? False sharing. False sharing. Ooh, now I got a tough one. Okay, well we get to hold the book for a little bit, and I'll tell you what the false sharing is. This is one of those times when you're threading and you have to know a little bit about the CPU architecture. If two pieces of data, completely unrelated, happen to end up in memory right next to each other, okay? This chunk of data is for thread 2, this chunk of data is for thread 1. Okay? They end up in the same, right next to each other in memory. The likelihood is that they will end up in the same cache line of the system as well. Okay? So every core, they define where all the cache lines are the same. So, if those two pieces of data are read and written by different threads, that means that that cache line has to move between different cores. So thread 1 is on core 1, thread 2 is on core 2. Thread 1 starts to write it, say, okay, I have to throw out the cache line from core 2. Boom. Right? And only this guy can write it. So he writes it, and then in core 2 says, well, I need to write my data. So this guy has to flush it out to memory, and then it brings it back in, and this guy gets to write it. Okay? So the data is completely unrelated, but they happen to be next to each other. This is called false sharing. They're sharing a cache line, or a chunk of memory, but they don't need to. Okay? This can kill your multi-threaded performance like that. it can drop you 10x easily. Because flushing a cache line out to memory is very slow. Same for the other thread. Because it has to flush out to memory, come back into the other core, flush out, come back in, etc. Okay? It's a very nasty problem. When does this problem happen? Classic example. You're doing multi-threaded programming, you create a structure of parameters, right? Input parameters and output parameters for your thread to work on, typically, right? Say, okay, I create a nice structure, I got a bunch of things that have to go in, and a bunch of things that come out from that thread working. Oh, and I got a whole bunch of threads. I got in threads, right? So I create an array of those structures, right? And likelihood is you put all the inputs first and all the outputs second in this structure. So the next structure's inputs are right next to the outputs of the other one. So you're going to be reading and writing, most likely, some of those cache lines that are right next to each other. Classic example. If you do that structure thing, an array of structures for parameters, very simple way to fix it. Cache a line or buffer fill out the fill out the structure to match a cache line. Okay? Now you can have that, by the way, you can have that problem at Java level, you can have it at C level or .NET level. Okay? It doesn't matter what programming language you're using, but if those two data end up next to each other and then bounce back and forth between cache lines. Question?
You would have to know a little bit about the CPU architecture you're running on. Can you always be sure that, or is it on most processors that it's, what is it,
64 bytes.
64 bytes?
Yeah, most x86 processors is 64 bytes. It's not easy to check it all the time. Basically, if you look at your threaded performance and you can't find another good reason why the threaded performance sucks, like you've eliminated the synchronization problems and the load imbalance, and then this is one of the things you start to look at. It's not a frequently common problem, but it's something that you can definitely run into. And then you start looking at where those structures are. There are some things on the Intel processor and another tool that we have called vTune Performance Profiler that can actually find this a little bit. Yeah.
What if I have a data structure that is actually shared by two threads? Is it synchronous? Is it loaded in both cores into the core-specific thread, or what happens then?
If you have a data structure that's shared by two threads, the cache lines can be, if nobody's writing them, they're only read, they can be in both cores. If somebody starts to write one of those parts of data, then the other one, whoever's writing it, will get exclusive access to write, and the other one will have to flush it, will trash it basically.
Okay, that's...
Does that make sense?
Yes.
Yeah. Was there another question?
Just a comment. I think there's another program which actually is able to read out certain registers from the CPU, actually saying how many cache flushes and stuff actually happen. So you can check those parameters if they are abnormally high.
Yeah, he's making a very valid point. With the vTune Performance Analyzer or the performance counters, you can read out how much cache flushes and for what the reasons they are. So tracking that will usually give you a good idea of what's happening. Usually L2 cache misses, spiking, is a good sign that you're false sharing, because that's just the generic one that captures all of those kinds of problems. If L2 cache flushes go up really, really high, then there's a good chance it's false sharing. It could also, though, unfortunately, it can be the case where when you go from single-threaded to two threads, that your working data set size is bigger than the cache for each of them. So you could kind of fall out of cache, as we call it. And so you can pay that same number of L2 cache misses. But we can talk about it a little bit more if you want. Okay. How am I doing on time? Okay. So now I gave you a quick overview of the thread building blocks. What we do here with thread building blocks, instead of specifying the threads, we specify the tasks. And we let the task scheduler deal with scheduling them however we see fit, or however it sees fit. Okay? We're going to specify one render thread ourselves. Okay? That's our render thread. And then the other we'll specify via task. So here's our main task. I'm going to specify a physics task, a particle task, and an AI task. Okay? We won't decompose the physics or a particle task, but we will decompose the AI task. Okay? I'm going to say, okay, here's an AI subtask. Okay, I can have as many of these as I want, potentially. And then I synchronize against what's called a continuation task. Okay? When they're done, they synchronize back there. When all of them are back, they synchronize against the sync task. And that would be the synchronization with the render thread, essentially. Does that make sense? Now when we look at it, lots of dark green. Lots of dark green is very good. Okay? You can see our concurrency level is up at 4 mostly. We have a little bit of time down here in the other threads, but much, much better. .66 seconds. Which is actually pretty good. It's 8.66 is 2.3-ish, 2.4. That starts to get good for 4 cores. For a problem that is not data parallel, a problem that is very functionally parallel. Okay? Now, for the last book, what would I do next to try and improve this performance even further? Yes. Who said that? There you go. You got a book. You can get the shirt. Yep. So obviously, now I go after those other functional tasks, physics and particles, and try to break them up into a data parallel way with more subtasks. Okay? Okay. So let me just reiterate here. This example that I've just kind of walked through is available in our software network. You can download the source code and everything. You can look at it. You can run it between single thread, multiple threads, and you can see exactly how it works, both with what we did originally, a Windows thread version, how much trouble it is, and then there's a thread building blocks version of it as well. Okay? So, what should you not use thread building blocks for? I/O-bound threads are probably not one that you want to schedule as tasks, because inherently the task scheduler treats tasks as compute-bound. Okay? You probably don't want to use it for hard real-time processing. Okay? If you need to have something happen in 5 milliseconds and scheduled, then you don't want to do it this way. If you're looking for soft real-time, you're generally okay with the thread building blocks, but generally hard real-time, not. If you have excessive usage of explicit synchronization, you'll probably run into some problems as well. Okay? Generally, if you have explicit use of a lot of synchronization, you've got more problems in figuring out whether it's TBB or Windows 32 threads. Okay? When you're synchronizing a lot, then your problem is inherently difficult to parallelize. And the neat thing is you can use it with Windows POSIX threads, P threads. You can use it with OpenMP. You can intermix them. You can tell TBB that I'm going to keep 2 threads for Windows. So, don't assume that you have all 4 cores. You only get 2 cores, and the other 2 I keep for myself to use somewhere else in the application. So you have complete flexibility from that perspective. Okay? Adaptive tuning for the load balancing. 1 scheduled thread per hardware thread. That's a very important part here. The scheduler that we have is really smart. It tries to balance where to steal tasks from and how often to steal tasks. It's not just steal the one from somewhere else. You actually don't want to steal the front of the queue. You want to steal the back of the queue, of course, so that you don't interact with the current CPU. You may try to steal only the core that's nearest to you that has a shared cache, by the way, because that means you can reuse the cache quite a bit more. So all these hardware details that it tries to take care of for you. And hey, it's open source. I encourage you to try it and give it a run. You can get it on threadbuildingblocks.org. And I think you'll find this a very powerful framework. It takes a little getting used to, but it's very easy. So the question?
Yes, hi. A lot of us are very concerned about the size of our programs, obviously, because we're here to code 64K demos and 4K demos. What would be the size of a program written with this library? A typical size?
Typical size of the library. That's a good question. What is the typical size of the library? I think, I'll be fair, I think it's close to 100K.
Right.
Which is a challenge for you.
That would be a challenge.
Well, I tell you one thing. There's two things here. One, it's open source, so you could write a trim. You could look at it and trim it down for what you don't need. There are parts of it that are already broken up a little bit. The concurrent containers can be separated out from the task scheduler, and the memory allocator can be separated out as well. Okay.
Just a quick question. What's the license? Is it really free or is it free for
GPL?
commercial use?
It's LGPL, I believe.
So not free for commercial use. It is?
Yeah, yeah.
Oh, yeah, okay.
Right. So you can link in. If you link it as a library, then it doesn't matter what you do with your source code, what you do with your code. If you modify it, then you have to share out. Another question?
Okay, maybe it's a stupid question, but and it's processor independent, so it works also non-Intel processors.
Yes. Yeah.
Okay.
Absolutely. This is one of the key reasons that we made it open source, actually. Not only processor, but language, right? We wrote this for C, C++, right? It's a monumental effort to go do it for Java and .NET and a few other languages. We said, you know what? Those other people want it. Why don't we put it out there so that they can do it? And there's already people actively working on Java and .NET ports. There's an IBM Power port. There's an Xbox 360 port. So there's quite a few people that are working on porting it. Between the other x86 architectures, there's no difference.
What was the profiler that you were using?
Sorry?
What was the profiler that you were using?
The profiler that I was using is called the Intel Thread Profiler. Okay.
Was it part of VTune or is it different?
It plugs into VTune. It's an add-on for VTune. I've got a bunch of CDs that have demo versions of all the tools. If you guys want to grab them, after the session is over, you can take a look at it. I think also there's going to be some licenses that are being part of the awards for some of the competitions in the next couple of days as well. Okay. Any other questions?
Earlier in your presentation, you were talking about the scalable allocator, which has a memory pool per thread. Is it safe to exchange memory blocks allocated in one thread, and, for instance, free them?
Is it safe to allocate memory from one thread and free it from another thread? I don't know. Might have to check. Off the top of my head, I'm not sure. I suspect that we did make it okay, but there's a big performance penalty for doing it. Right? Yeah, I'll look that up. It's kind of interesting. I'm not sure. I think that usually you try not to do that, right?
Yeah.
Right. If you have memory allocation per thread, you want to keep it all within your thread. Any other questions? Okay. Please come up. I've got a. Oh, I guess I need to give this a last. Who would like it first? We got. There you go. This is a O'Reilly book that was published already for the Intel Thread building blocks. I encourage you to download it, take a look at it. It's quite powerful. The demo that I talked about here is also available online on our software network. And I have a bunch of sample CDs if you guys want to try the tools out as well. Okay? Thank you very much for your time.